Now that we've seen the graphs of all 6 trig functions, I want to start talking about inverse trig functions, functions that will actually undo all of these trig functions. And so we're going to take a look really quickly at the graphs and why we can have these inverse functions, and then we'll get into the analytics of actually finding the inverses. So remember, for a function to have an inverse, the original function has to be 1 to 1. It has to pass the horizontal line test. If it doesn't pass the horizontal line test, then it cannot have an inverse. On some functions, what we decided to do in order to talk about an inverse was to restrict the domain. So if we restrict the domain of these trig functions, sine and cosine, then we can have an inverse function. So here's the graph of the parent sine function, and we can clearly see it will not pass a horizontal line test at all. If I draw a horizontal line along here, I'm going to intersect that graph infinitely many times. So what we do is we look for a piece of the graph that will be 1 to 1. And see the red box, the graph inside the red box? If I restrict the domain to negative pi over 2 to positive pi over 2, that piece will definitely pass my horizontal line test, and therefore I can talk about sine having an inverse function. So when we have inverse functions, remember the domains and the ranges of those inverse functions are swapped. So let's talk about, this is kind of stretched out, but let's talk about the sine inverse function. Let's talk about the domain. So remember, we'll just say if we have a function f of x and it has a domain, the inverse of that function, the domain of the original, will become the range of the inverse, and the range of the original will become the domain of the inverse. So you can see now along the y-axis we are drawing angle measures, because the outputs of these inverse functions, the outputs are going to be angle measures, and the inputs are going to be those integer values that were normally along the y-axis. So for the sine function, the domain was angle measures, but the range was side ratios. Square roots of 2 over 2, square roots of 3 over 2, 1/2. So what's going to happen for sine inverse of x is the domain now becomes those side ratios, and the range, the y values of this function, are now angle measures. So we just have to keep that in mind. So the domain of this restricted sine inverse function is the range of the original sine function, and that's negative 1 to 1. The range, since we restricted the domain, is negative pi over 2 to positive pi over 2. And that came from that red box that we just took that little piece of the sine function, and then we reflected that over the line y equals x in the plane, just like we did the other functions. So here is what the original sine function would look like. There is y equals the sine of x, and when we reflect that over the line y equals x, we get the graph of y equals the sine inverse of x. There is an alternate terminology for inverse when you're talking about trig functions, and it's called the arc. So if you see the arc sine of x, it is just an equivalent way, an alternate way to write the sine inverse of x. So we have arc sine, arc cosine, arc tangent. those kinds of things. So again, here is the graph of the parent cosine function. We can clearly see again it is not one-to-one. It would not pass the horizontal line test. So we choose to restrict the domain, and here on cosine we restrict the domain from 0 to pi. We just take that one little piece, and then that will pass the horizontal line test, and we can talk about cosine having an inverse function. Again, the domains and the ranges are switched, so let's talk again. Here, if we had h of x equals cosine of x, the domain for that function would be angle measures. And we know that from our unit circle work. The range is there for side ratios of those triangles that we drew. So if we talk about g of x being the inverse of cosine, that's cosine inverse of x, and its domain is the range of cosine. So we're going to be putting side ratios into this function machine, and the range is going to be those original angle measures, because inverses undo each other. This maps us back to where we started. So again, we shouldn't be surprised that our y-axis is values from 0 to pi, or angle measures, and our x-axis is -1 to 1, or what were originally range values. So the domain for cosine inverse is -1 to 1, while the range for cosine inverse is 0 to pi. So now that we've looked at the graphs and seen what's going on there, let's get down to actually evaluating inverse functions. So if I have a function y equals the sine inverse of x, and I tell you that our x value is 1, remember that is a side ratio. The answer to this question is going to be an angle measure. So the easiest way to solve these inverse trig problems is to ask yourself a question. For what angle does sine have a value of 1? Now we need to make sure that angle is in the original domain of sine, because that's what we're mapping back to, right? We're mapping back to those angle measures. And so remember from the unit circle, if we're looking for where sine has a value of 1, that's right here in the unit circle, and that is an angle measure of pi over 2. So to solve these inverse functions, you're going to go back to the unit circle and back to the original function to see what that angle measure was where that side ratio occurred. So the sine inverse of 1 is pi over 2. Let's look at this one. We're going to do the same thing here. We're going to ask ourselves, in that unit circle, for what values was cosine 0? Well, cosine is 0 here, and cosine is 0 here. But remember, we can only go and get those values that are between 0 and pi, because cosine inverse has a restricted domain. So between 0 and pi, this is the only angle measure where cosine had a value of 0. Let's work a couple more examples here. Here is the sine inverse of square roots of 2 over 2. So for what angle measure was sine positive root 2 over 2 from negative pi over 2 to positive pi over 2? Let's go back to that unit circle. We know that's going to be some iteration of pi over 4. We are in this quadrant and we are in this quadrant. Here is negative pi over 2, and here is positive pi over 2. And we're talking about sine, so we're looking for the y values, and we know that here we had a y value of positive root 2 over 2. Here we had a y value of negative root 2 over 2. So once again, we're talking about, sorry, right here, we're talking about this angle measure. It's the only place on that interval where sine was positive root 2 over 2. So on these inverse functions, we're going to get angle measures for an answer. Angle measures are going to be our answer. Here's the cosine inverse of -1. Let's go back to the unit circle. We are restricted to values between 0 and pi, and we want to know where cosine was -1. That happens right here. The coordinates of that point are -1, 0. Cosine was -1 when the angle measure was pi. So the unit circle is going to help us a whole lot when it comes to doing these inverses. Remember that if I have a function and I compose it with its inverse, it will always map me back to where I started. It's going to map me back to x. I can compose an inverse function with its original function, and it will map me back to where I started. The only thing we're going to have to pay strict attention to is that we have restricted the domain. So we're going to have to pay attention to whether this was in our original domain. So we work inside. The first step is to work inside. So the first thing I want to find is the sine inverse of 1. Well, we found that in a previous problem. If you'll remember, that was pi over 2. So now what this is saying is now this is equal to pi over 2. So what I'm actually after is the sine of pi over 2. And the sine of pi over 2 from the unit circle is 1. So can you see that when I compose sine with its inverse, it just gives me what's right here. The sine of the sine inverse equals 1. Moreover, the sine inverse of sine of pi over 2, because we put angle measures in sine, right, would give me pi over 2, because this is going to give me a value of 1, and the sine inverse of 1 is pi over 2. So everything that we know about inverses and composing a function with its inverse, all of that is still true. We don't necessarily just have to compose a function with its inverse. We can answer questions like this. We can look inside and start working inside. The first thing that we want to find is the cosine inverse of positive root 3 over 2. Remember that our domain has to lie between 0 and pi. We're looking for an angle measure on that domain. So we go to the unit circle. We look for where cosine is positive root 3 over 2. That happens here at pi over 6, and we're from 0 to pi. So over here at 5 pi over 6, cosine is negative root 3 over 2. So this is the only possible solution. So this is pi over 6. This equals what's inside equals pi over 6. So now what I need to find is the sine of pi over 6. And that from the unit circle, we remember, is positive 1/2. So these are not difficult questions to answer. We just need to make sure we're careful that we have restricted that domain. So let's start with a cosine of 5 pi over 3. 5 pi over 3 is here in quadrant 3. And so that is where cosine is the smaller measure, and it is negative, so that is negative 1/2. I disagree. Let's see. Nope, I'm sorry. I'm at 4 pi over 3. Woo, you got to watch me. 5 pi over 3 is over here, so they are correct. There's 5 pi over 3. The cosine value would be positive 1/2. So now I'm going to put positive 1/2 in the cosine inverse function. And let's go back to cosine. And I can only look for values between 0 and pi, and I'm looking for where cosine is 1/2. That happens here at pi over 3, and it happens here at 2 pi over 3.